and my project's objective was to determine the optimal pH for the enzyme papain in the digestion of protein substrates, milk, gelatin, and egg whites. Papain is widely used in various industries such as food processing, for tenderizing meat and clarifying beer and juices. In medicine, it's used for wound healing and digestion, and in cosmetics, it's found in whitening toothpastes and face creams. Understanding its optimal pH is crucial for maximizing its efficiency. My hypothesis was that the optimal pH for papain would be at a slightly acidic to a neutral range, pH 6 to 7. So I conducted an experiment. I prepared the protein substrates, milk, gelatin, and egg whites first, and then the pH buffer solutions 3 to 8 were prepared by Dr. Groh, and the test tubes were labeled 1 through 8 for each pH level, and there were 6 pH levels, uh, and the papain enzyme solution was prepared by mixing 0.5 grams of papain powder with 10 milliliters of distilled water, so it's a 5% stock solution. And I added buffer to all of the test tubes, and I added the protein substrates to test tubes 1 through 6. So 1 and 2 contained milk, 3 and 4 contained gelatin, and 5 and 6 contained egg whites. The papain enzyme solution was added to the odd numbers 1, 3, 5, and 7. So it was like with enzyme and without enzyme. And test tube 7 was a enzyme and buffer control, and test tube 8 was a buffer control. So I mixed all of the test tubes, and I let them sit in a water bath at 37 degrees Celsius for 45 minutes. And then I conducted the biuret test, which is a colorimetric assay that detects the presence of proteins and peptide bonds. The positive result is indicated by a purplish color, and the negative result is indicated by a light blue color. And then I measured the absorbance values at 540 nanometers using a spectrophotometer, and I calculated the absorbance difference using the formula at the bottom on the left corner. It's also for the mean of 3 trials. So the photos you see are from the biuret test, and the tables are the results of the biuret test, and the test tubes 1 through 6, which contain the protein substrates, are all positive, but test tube 7 and 8 are negative because they didn't contain any substrates. And these tables over here at the top are the spectrophotometry absorbance values, and I'm not sure if I can zoom in, but I have the numbers memorized. So let's take an example of calculating the absorbance difference. So for milk, pH 3, it is 0.943. Delta A equals A with papain, minus A without papain is the equation. So A with papain is 0.943, and A without papain is 1.305, and the difference between them is negative 0.362. That's the absorbance difference. And it's also here in this I can't zoom in. Okay, it's here in this table under the absorbance differences and average under the milk absorbance. And you see that the average of trials 1, 2, and 3 is negative 0.118. And it is also in the graphing analysis. So in the bar graphs, the higher the positive difference, the more enzymatic activity. So whichever one is the highest is the optimal pH. So for milk, we see it's pH 5. For gelatin, it's pH 7, and for egg whites, it's pH 6. So that's the conclusion. But some errors were made, such as lactose interference in milk samples. An orange color was produced in the milk samples. Because lactose is a reducing sugar. The Bradford assay was the initial option, but since it wasn't available, I used the biuret test. And then in trial 3 pH 7, the gelatin was the results were counted as negative because of an incorrect substrate measurement, and the biuret test was extended for 12 hours due to time constraints. Usually it takes 15 to 30 minutes, and in trial 3, pH 8 resulted in a blank entry as there was no buffer left. Um, So those are the errors, but overall, this experiment proved the hypothesis and also provided valuable insights to research and industrial applications, especially food processing, as I tested on protein substrates. Thank you.